Hello everyone, welcome to Probability and Statistics for Data Science. Today we're going to talk about modeling discrete and continuous data. The prerequisites for this material are discrete multivariate random variables and continuous multivariate random variables. Our goal is going to be to learn to manipulate discrete and continuous quantities within the same probabilistic model. Let's start with the mathematical definition. We're going to consider that we have a discrete random variable which is going to model a discrete quantity of interest. That is going to be D, and a continuous random variable which is going to be C, which models a continuous quantity of interest, a real valued uncertain quantity that we're interested in. The way we construct random variables from the mathematical point of view are as functions from a sample space to either a discrete set of values in the case of discrete random variables or to the reals in the case of continuous random variables. So I always say the same thing. This is just a mathematical framework underlying all of the tools that we build later on. And in general, when we manipulate random variables, we just use PDFs, PMFs. We don't really think of this underlying probability space. We don't even build it explicitly. But in order to build everything mathematically with a reasonable foundation, we have to talk about it, at least at the beginning. Okay? So what happens is that there is a sample space here. And the way we model the fact that the discrete quantity and the continuous quantity are related is that they map outcomes in this, they map outcomes in the sample space to values simultaneously. So what do I mean by that? Let's take first the discrete random variable. To make our life easy, let's just imagine that the discrete random variable can only take two values, like 1 and 2. Okay, in general, it could take a discrete set of values, 1, 2, 3, 4, 5, 6, 7, or even countably infinite, but let's just imagine. So here in particular, this value gets mapped to 2, this value also gets mapped to 2, and this value gets mapped to 1. Okay, these outcomes within the original probability space, within the sample space of the probability space. At the same time, we have another random variable C. Okay, and just to make things clear, this is D. We have a continuous random variable C that models a continuous quantity. So that continuous quantity is going to take values on the real line. Okay, and maybe this guy takes this value, this outcome is mapped to this other value, and this other outcome is mapped to this other value. So now we can talk about situations where D is equal to 2 and the continuous variable C is equal to this, I don't know, whatever this value is, like maybe 10. Here D is equal to 1 and C is equal to, let's say, 20, and D is equal to 2 and the continuous value is equal to, let's say, 40, for example. So just to be clear, this is the continuous mapping. Okay, so how do we characterize this joint distribution? Can we define a joint PMF? We could define a joint PMF if this guy here had a discrete set of values, because then we could say, oh, what's the probability of this discrete set of possibilities, right? But that's not the case, because the continuous random variable can take a continuous, can take continuous values. So we cannot compute a joint PMF. When we look at the probabilities, we're going to have exactly the same problem as when we considered using probabilities to describe continuous random variables. The probabilities are going to be equal to 0 because there's just uncountably infinite possibilities, right? There's uncountably infinite possibilities there. So we're not going to be able to define a joint PMF. Can we define a joint PDF? So let's take a look at the possible values that we can get. The possible values that we can get is, for D, it's easy, right? It's only 1 or 2. For C, it's all of this real line. So if you think about it, we could have any real value for d equals 1 and any real value for d equals 2. Okay, those are the, maybe I'll do some straight lines, won't be sloppy. So, okay, every possible real value for d equals 1, every possible real value for d equals 2. Can we define a density? We cannot define a 2D density. Why? Because here in this axis, in the discrete axis, we only have a discrete set of values. So we cannot define a 2D density that can be integrated to give us probabilities. So what do? The joint PMF doesn't make sense, the joint PDF doesn't make sense. However, related to the joint PMF and the joint PDF, we talked about marginal and conditional distributions. So we could think, do these make sense in our case? And actually they make a lot of sense, right? Because to start with, of course, there's a marginal PMF. That's just the probability that we end up here. It's, you know, the set of points here that map to 1 or to 2. So definitely there's a marginal PMF of D. We definitely have a density here. So there's a marginal PDF of C, right? And we can reason about the probability of ending up in every possible interval. That's how we're going to get the density. So there's definitely a marginal PDF of C. Now we can also think, is there a conditional PDF of C? The conditional PDF of C if we condition on D. And actually there is, right? Because imagine like we only think about the points that map to 2. Then we can reason about what is the probability that they end up in any certain interval of the real line when they're mapped through C. So the conditional of C with respect to d equals 2 or d equals 1 is actually a density. I mean, you can see here that it's, we'll see in more detail in a moment, but this is just to give you a quick intuition that the conditional density actually makes sense. In the same way, say, okay, so now, you know, let's consider the possibility that we end up here. You know, what is the probability that d is equal to 1 or 2? That one is a little bit trickier, right? Because we're conditioning on a point that has 0 probability. The probability that a continuous random variable takes a specific point is equal to 0. So that one's going to be a bit tricky, but we're going to see that we're going to be able to define it using limits in a very similar way to how we defined the conditional density conditioned on a continuous random variable taking a specific point. So long story short, what happens when we try to model continuous and discrete random variables at the same time is that we realize that the joint PMF and the joint PDF do not make sense anymore, but conditionals and marginals do. And that's what we're going to do. We're going to work with the conditional and marginal distributions. Okay, so joint PMF and joint PDF don't make sense, but the marginals and the conditionals do make sense, and that's what we're going to use to manipulate discrete and continuous random variables together. Okay, so let's start with the conditional CDF and PDF of a continuous random variable given a fixed value for a discrete random variable. The events C is smaller than a certain value. Okay, so let me go back to my picture for a moment. So we can think of the event C is smaller than a certain value, so C is here. And at the same time, D is equal to, let's say, 1. Okay, we can go back here and see, oh, from all of these points that get mapped to 1, how many of them are mapped, maybe I should have done this in red, are mapped to values for which the random variable C is smaller than a certain value. So this could be like maybe this part. That event is going to be assigned a probability in the underlying probability space. Why? Because the continuous random variable is a valid random variable. So this, because the continuous random variable is a valid random variable. So all the points for which the random variable is smaller than this value are a valid event. And the discrete random variable is a valid random variable. So all points for which d equals 1 is a valid event. And now this red thing, which probably I should have drawn in green because it's a joint kind of thing, this set where d is equal to 1 and the continuous random variable is smaller than this certain variable, this certain value c, that's the intersection of two events that are well defined. Okay, and because of that, we can now reason about the probability that the random variable c is smaller than that fixed value, conditioned on the discrete random variable being equal to a certain value. Okay, that is going to be well defined as long as the discrete random variable indeed can take that value. And the reason it's well defined, again, is because it's an intersection of two well defined events in an underlying probability space. Since it is well defined, we can just say the conditional CDF of C conditioned on D taking that particular value is equal to that probability. Okay, so we have a conditional CDF. We are happy because we can do this for every possible value on the real line. What's the probability that the continuous random variable is smaller than that, given that the discrete random variable is equal to each of its possible values? Okay, that's the conditional CDF. And now very naturally we can say, oh, so now what's the density, right? What's the probability that we're in a small interval, given that the discrete random variable has a certain value? So if we go back to my picture, which is getting a little bit messy, what we're saying is, okay, assume that d is equal to 1. What's the probability that I am here? Okay. The probability that I am in that very small interval divided by the length of the interval, that gives me a density. And that's how we manipulate continuous random variables, right? Using densities. So I can consider that density where I'm dividing by the length of the interval, and that is just going to be equal to the probability of that interval, which is obtained by the CDF at the ends of the interval. This is exactly the same thing we did when we considered the density of a continuous random variable. And then we can see immediately that that density is just going to be the derivative of the conditional CDF. So we have a conditional CDF that is well defined, and we do if the discrete random variable and the continuous random variable are well defined. If that CDF is differentiable, then we can get a conditional PDF. And that's usually how we're going to manipulate continuous random variables conditioned on discrete random variables with the conditional PDF. Let's take a look at an example. Here we're looking at temperature and precipitation, where precipitation can be 1 if it snows or rains, or 0 if there's no precipitation. And the temperature can be continuous values. Okay, in this case in degrees Celsius, because I don't really understand Fahrenheit very well. Okay, so I used kernel density estimation to estimate these conditional PDFs from data where each data point was a temperature and a 1 or a 0, which basically represent whether it was raining or snowing or not at that particular moment where that temperature was measured. Okay, and if we look at the temperatures when, maybe I'll highlight it. If we look at the temperatures, I forgot to say, this is in Mauna Loa in a volcano. There's a weather station up in a volcano in Hawaii, in Hawaii's Big Island. And that's a weather station I chose for this example. When it's raining or snowing, you can see that the temperatures are either low, close to 0, or they're around 10, mostly when it's raining. When it's not, or snowing, right here probably it's snowing. When it's not, there's no precipitation, then the temperatures are not as cold, and it gets warmer. So apparently when it's quite warm, you see here that when it's quite warm, it doesn't seem to, that looks a bit ugly. Yeah, let me try again. Actually, let me use something else to highlight. So when it doesn't rain, the temperature is slightly warmer, and there's this unimodal, like the distribution has just one maximum. It's interesting that when there is precipitation, it has kind of two maxima. I think that probably the lowest one is when it snows, and the higher one is when it rains, but that data is not there, or at least, maybe it is there, but I was lazy and I didn't look at it in detail. That would be something interesting to look at. Anyway, so this gives us the conditional densities of this continuous quantity, which is temperature, given precipitation, which can be either 1 or 0. Okay, there's precipitation or there's no precipitation. And this was in 2015, this data for 2015. Okay, so now imagine that we have the conditional PDF of the continuous random variable given the discrete random variable for each possible value of the discrete random variable. How do we compute the marginal distribution of the continuous random variable? Okay, so we want the CDF of C. That's just the probability that the continuous random variable is smaller than a certain value. And what we can do here is just apply the law of total probability and say, well, this is just equal to the union of the continuous variable being smaller than that particular value, intersection, okay, here, if we want to go even have an extra step, you could say, well, this is equal to C being smaller or equal to that particular value, intersection D having every possible value it could have, okay? So here we're summing over every possible value that D could have. And then you can split this using the chain rule. That's the law of total probability. I tend to like to, do things step by step. But anyways, now we see that essentially here, what do we have here? This is just the conditional CDF. So we have a weighted sum of conditional CDFs. If we're interested in the densities, we just need to differentiate this guy to get the density of the continuous random variable. What's going to happen? Well, the only dependence here is through the conditional CDF, so we're going to end up with a weighted sum of conditional PDFs. This is kind of interesting because if you remember, if you want to compute a CDF of, let's say C1, if you have the joint distribution of C1 and C2, where these are two continuous random variables, then what we did is we integrated over C2 the joint, right? The joint distribution, the joint CDFs, the joint PDF of C1 and C2, we integrated it over C2. And when we had two discrete random variables, we summed over the random variable that we were not interested in to get the marginal. Well, here it's kind of a mixture of both, right? So we have this, which is not a joint PDF or a joint PMF, but it's close in the sense that we have a marginal and we have a conditional, and then we sum over the variable that we don't want. So we start seeing that this guy, in some ways, is a little bit of a surrogate, this product of the marginal PMF and the conditional PDF. That's kind of a surrogate for a joint PDF or PMF. It's not a joint PDF, it's not a joint PMF, but you sum over it to obtain the marginal. So, Okay, so let's take a look at the example of the Mauna Loa volcano. So I already showed you the conditional PDFs when we had precipitation and we did not, and when we did not have precipitation. Now it turns out that it doesn't actually. I'm surprised because I know that in Hawaii it rains a lot, but this is at a very high altitude. So maybe because of the altitude, it actually snows or rains very, very rarely. I think that's like 3% of the time. So what's going to happen when we combine these guys to compute the density? We're going to multiply. So what are we going to do? By the formula that we have just derived, we're going to multiply this conditional PDF by this value. And I hope I'm getting the colors right. Actually, I'm using a completely different color for this one, so whatever. And this value by this guy, right? That's what we're going to do. This is how we're going to compute the marginal PDF of the temperature by the formula that I just computed. Of course, in practice, you can just do kernel density estimation over the temperature values. Okay, so you don't really need to do this in this case to compute the marginal of the temperature. But this is just to show you what the formula that we have just derived actually means for the Mauna Loa example. It means that to get the marginal PDF, you would multiply the blue density times the blue value, so very, very small, and the purple density times the purple value, which is much higher. What's going to happen? We're going to end up with a marginal that looks like the purple density. Okay, this is what I was saying here. You're going to multiply the probability of 0 times the conditional density given 0. You're going to multiply, am I getting that right? Yes, the colors are right. We are going to get the probability of 1 times the density given 1, and you end up with something that looks essentially like the density given 0, just because this is much, much larger than the probability of 1 in this case. Let's look at another example. In this example, a biologist is studying the weight of grizzly bears in Yellowstone, and she determines that males have a weight that is approximately Gaussian with parameters mu equals to 240. Remember, that's where the Gaussian is centered, and a standard deviation of 40. That tells us how the Gaussian is stretched out. Okay, this is the conditional, just to be clear, this is the conditional distribution given that the grizzly bear is a male. And if the grizzly bear is a female, then the distribution over just the females is also Gaussian with a smaller mean, because apparently female grizzly bears tend to be smaller, and a smaller standard deviation. Okay, so the Gaussian is also going to be thinner. And there's about the same number of females and males. This is basically telling us the marginal PMF of the sex of the grizzly bears. So there's a kind of a probability 1/2 of having a male or a female grizzly bear. Okay, so now what if with this information we want to compute how the density of weight for all grizzly bears look like? So we define, this is actually going to be a Gaussian mixture. You might have heard of Gaussian mixture models, which are used to perform clustering. Well, this is going to be a Gaussian mixture model. We'll see in a moment why it's called a Gaussian mixture model. We define a discrete random variable S, which represents the sex of the grizzly, and a continuous random variable W, which is the weight of the grizzly. And now we want the marginal of W. What do? We sum the conditional densities weighted by the corresponding marginal PMF of S, right? So the probability of S times the density of the weight given, the probability of S equals 0 times the density given S equals 0, the probability of S equals 1 times the density that given S equals 1. So this is the probability of male given that times the density of the weight given that the animal is a male, plus the probability of female times the density of weight given that the grizzly bear is a female. This guy was a Gaussian, this is a Gaussian, they're weighted by 1/2 each, and this is what we get. Okay, so the picture is this. This is the distribution. This is the distribution for females, which they're smaller, so that's why the Gaussian is shifted to the left. It's a bit thinner, it has smaller standard deviation. This is the distribution for males. They're bigger, they weigh more, and there's a larger standard deviation. And the purple curve is the distribution for the whole population, which makes a lot of sense, right? You have the females and the males, so there's like kind of two humps. This is why this is called a mixture of Gaussians, because we're taking two Gaussians and we're mixing them together. And that's how the marginal PDF looks like in this case. Okay, so now we have talked about the conditional distribution of the continuous random variable given the discrete random variable. What about the conditional distribution of the discrete random variable given the continuous random variable? Okay, so here we're going to run into this problem that I mentioned briefly at the beginning. We want to condition on the continuous random variable being equal to a fixed value. And we have already talked about this when we talked about the distribution of the conditional distribution of a continuous random variable given another continuous random variable. The problem that we have is that the probability that the continuous random variable is equal to a fixed value is actually 0. So, and conditional probability is conditioned on events of probability 0 are not well defined. So what we do? As often, we use limits. So here, let me very quickly recreate my picture. So we had that the random variable, let's say, let's say that the discrete random variable can only be equal to 1 or 2, and then the continuous random variable can be equal to anything on the real line. What we're saying here is, okay, we want the probability that we are here, okay, as opposed to here, let's say, for this value of the continuous random variable, but the problem is that we cannot condition on this specific point, because that specific point, the probability that the continuous random variable ends up in that specific point is 0. So what do we do? What we do is we consider a small interval around it, actually an interval before it, with epsilon, and then we reason with that interval, and then we collapse the interval to 0. That's what we're going to do. Okay, and this is exactly the same reasoning that we applied when we define the conditional PDF of a continuous random variable given another continuous random variable. Okay, so we have the probability of 1, the probability that the discrete random variable is equal to 1 or 2. We're going to condition on an event where the continuous random variable is in this small interval of with epsilon, and then we're going to take the epsilon to 0. That is how we're going to define the conditional PMF of the discrete random variable given a specific value for the continuous random variable. Okay, so now let us imagine, so we already learned how to get the conditional, the marginal density when we knew the marginal of the discrete random variable and the conditional of the continuous random variable given the discrete random variable. How about the other way around? Imagine that you know the density, the marginal of the continuous, and you also know this conditional PMF that we just defined as this limit when this interval goes to 0. What if you know that? How do you compute the marginal distribution of D? So remember that before, okay, if we wanted the marginal of C, what did we do? We took the marginal of D, the conditional of C given D, and we summed over all the possible values of D. Well, it turns out that if you have the marginal of C and you have the conditional of D given C, you can actually integrate over all the possible values of C to get back the probability of D. So again, we have these two objects that look suspiciously, or that operate kind of like a joint PMF or a joint PDF, but not quite, because one is a density and the other one is a probability. We'll get back to this, but first let us actually prove that this is the case, okay? So we want to show that indeed, if you have the marginal of the continuous random variable and the conditional of the discrete random variable given the continuous random variable, if you integrate that over the continuous value, indeed, you're going to get back the probability that the discrete random variable is equal to this value D. How do we prove that? It gets a little bit tricky. The idea is that we're going to define a grid with a certain step size epsilon. So let me go to the picture again. Let's imagine that the random variable D can only have two values, 1 or 2. And I'm going to draw the real line here. And now what we're imagining is that we have the conditional probability that D is equal to all these possible values, okay? And what we're saying, conditioned obviously on each of these guys, and what we're saying is that if we integrate this weighted by the density of the continuous random variable, we're going to get back the probability that D is equal to 1. But the problem that we run into, as usual, is that well, it's not clear, right? It's not clear how to prove this because of how we have defined the conditional PMF in terms of this limit. So what we're going to do is we're going to say, okay, what if we were like in this, I should do that in blue, what if we're in these intervals, okay, in a discrete number of intervals with step size epsilon. So here, okay, we divide all of this in terms of epsilon. So the continuous random variable is in each of these intervals. And now we can ask ourselves, what is the probability that D is equal to, for example, 1? Well, if we divide the possible values of the continuous random variable, and we say, and we add over the random variable being in any of these intervals, okay, so we consider the event that the continuous random variable is in any of those intervals that completely cover the real line. Okay, this is important, they completely cover the real line. And we take the intersection between that and D being equal to D, then that's going to be equal to the probability that the discrete random variable is equal to 1. Okay, because that's the continuous random variable has to end up in some interval here. Okay, and because it has to end up in some interval here, I realize that I drew too many arrows. Sorry about that. But the continuous random variable has to end up in one of those intervals. So if we take the union of all the events that D is equal to that to 1, for example, and the continuous random variable is in one of those intervals, the union of all those events has to be the event that the discrete random variable is equal to 1 in this case. Okay, so that's where that formula comes from. And now what we can do is we can take the limit when epsilon goes to 0, and when epsilon goes to 0, this kind of sum, and this is getting into calculus, is equal to an integral where we have divided by epsilon to get a kind of density if you want, and now we have this differential of C, okay, where we make these C's, these discretized intervals, like when we make them 0, that sum eventually becomes an integral. And again, this is getting more into calculus, but once we have that integral, it's kind of nice because now we have the intersection between D equals D and this probability, and now we can split this by the chain rule. Actually, no, sorry, actually, that's not what I meant. We can actually multiply and divide. We can multiply and divide by the probability that the continuous random variable. So yeah, I got confused with a proof that we're going to do later on. Sorry about that. We're going to multiply and divide by the probability that the continuous random variable is each of the small intervals before taking the limit. Why do we do that? Because now we end up with a term here that is exactly equal to the conditional of D given the continuous random variable being in each of the small intervals. And here we end up with something that is actually the density of the random variable. So when we take the limit when epsilon goes to 0, this is actually just going to be f of c at c. This is just the density of the random variable. By definition, right, the density is the probability that you're in these intervals divided by the length of the interval. And here we have the probability that d is equal to d conditioned on, okay, here there's the intersection divided by the probability that the continuous random variable is in each of these small intervals. So we get the probability of the discrete random variable being equal to D conditioned on C being in this small interval. And that is exactly by definition just the conditional PMF. Okay, so actually this completes the proof. This got a little bit tricky in terms of integrals and limits and so on, but the intuition is basically that you have this object where you're basically weighting the conditional probabilities by the density and then aggregating them all together, because again, this object here acts like a kind of joint PDF, joint PMF. Okay, I hope that was more or less clear. So let's go to that point. We saw when we were discussing discrete random variables that the joint PMF can be written as the marginal of one of the random variables times the marginal PMF of one of the random variables times the conditional PMF of the other one given that one, or the other way around. So in terms of marginals times conditionals. For continuous random variables, we saw the same thing for the densities, right? So you take the density of A and B, it's the marginal of A times the conditional of B, or the other way around. So here, over and over and over again, we have been running into the marginal of the discrete random variable times the conditional density, so the marginal PMF times the conditional density, or the marginal PDF of the continuous random variable times the conditional PMF. So are they the same thing? This is, here on the left, is the object that we integrated to get the marginal PDF of the continuous random variable. The object on the right is, this is what we summed over D to get, not integrated, summed over D to get the marginal PDF of the continuous random variable. This is what we integrated over C to get the marginal PMF of the discrete random variable. In the same way that we sum these guys to get the marginals and we integrate these guys to get the marginals. So they, these objects act in that way. Can we actually prove that we have this equality? So let's try. We have the marginal of D, the marginal PMF of D times the conditional of C given D. What is this equal to? Well, it's the probability that D is equal to D by definition of the PMF, and the conditional density, which we have already seen. It's the probability that you're in this small interval divided by the length of the interval, conditioned on the discrete random variable being equal to that value. Great. So what do we do now? We take the limit outside, and now here we have a certain probability times a conditional. So by the chain rule, this is just equal to the intersection of the probability of the intersection of the events that the discrete random variable is equal to D and C is in that small interval. And now I can just apply the chain rule in the opposite direction. So this is just equal to the probability that C is in that interval times the conditional. But what has happened here? What has happened here is that I've ended up with, when I take the limit again, when epsilon goes to 0, I have ended up with this density. This is exactly the density of C, right? The probability that C is in a certain interval divided by the length of the interval. And on the other hand, I've ended up with our definition of the conditional PMF of D. So what is happening here? What's happening here is that it's difficult to deal with continuous random variables. We have to go to these limits where the intervals are very small. And what we do is we give ourselves a little bit of leeway. We say, okay, let's not go into, let's not go to the limit where the interval is infinitesimally small just yet. Okay, let's consider an interval that is of length epsilon. Once we have an interval that is of length epsilon, then we can work with probabilities, right? We can have a probability here, and then by the chain rule, we can take the conditional distributions in any direction, right? Like we can apply the chain rule in one direction or the other direction. And then when we take limits again, we come back to the density world for the continuous random variable. We come back to the density world for the continuous random variable. We see that indeed the marginal PDF of C times the conditional of D given C is exactly the same as the a marginal PMF of D times the condition. And this actually we're going to apply all the time. Let me give you an example where this is very useful. Imagine that for my Mauna Loa example, now I want to say, okay, I know the conditional density of precipitation when, sorry, not the conditional density of temperature when there is precipitation and when there is no precipitation. I know the PMF of precipitation. I know the marginal density of temperature. But what I really want to know is precipitation given temperature. If there's a certain temperature, I want to know the probability that it's going to snow or rain, okay, or not. And in order to do that, I need the probability, so I need the PMF of the discrete random variable given the continuous random variable. So how do I compute this? Well, I go back to the formula that we have just derived. This is just going to be the marginal of the discrete random variable times the conditional of the continuous random variable given the discrete random variable divided by the marginal of the continuous random variable. And I have all of this, right? This I can just estimate with empirical probabilities. You know, what fraction of time does it, is there precipitation, what fraction of time is there no precipitation. This I already showed you that we could estimate by KD. I look at the temperatures when there is precipitation or where there is no precipitation, and this I can also compute by KD. I look at all the temperatures and I just compute the density using kernel density estimation. Okay, so when we do that, this is what we obtain thanks to our formula. We see that when it's very hot, indeed, as we probably suspected from what we had seen before, the probability of no precipitation is almost 1. When it's cold, actually, the probability of precipitation is much higher. So it seems that when it's cold, it tends to snow, you know, like, I don't know, 25% of the time, 20% of the time. When it's hotter, it never rains. And then here in between, when you are kind of like, you know, your temperature is close to like 9 degrees, then there the probability of precipitation is higher, okay, than, for example, if you're at 5 degrees. Let's go to the other example, to the grizzlies in Yellowstone. You see, you know, you find a bear, you weigh it. It weighs 180 kilograms. What's the probability that they are male? Probably you can just look, right? But, you know, let's imagine that for some reason, maybe you kind of see through binoculars and for some reason you figure out how much it weighs. This seems a bit contrived, but, you know, what's the probability that bear is male? So what are we going to do? We want the probability of 0 given 180. Remember that 0 represents male. So the males are these guys and the females are these guys. And we know that we are here, right? 180. So we are here. So this is the value of the conditional density given 0 at 180. And maybe this is the value of the conditional density given 1 at 180. And what we're going to do is we're going to say that this is equal to the probability of 0 times the density at 0 by the formula that we just figured out. So here actually this is just 1/2, so it's not going to have much of an influence, divided by the marginal at 180. But remember that the marginal is just this guy plus this guy weighted by this. So at the end of the day, what are we looking at? Because the probability of the discrete random variable is equal to 1/2 for 0 and 1/2 to 1 for 1, basically what we're going to find is the ratio between these two numbers. Okay, that's what's going to give us the probability that the bear is a female. Okay, so let me write that down a bit cleaner. We want the probability of 0 given 180. We apply our formula. And now this guy, what I was saying is this is just equal to PS of 0 times PA of W, sorry, that probability of S equals 0 times the density of W given S at 0 plus the density at 1 times the probability of 1 times the density of 180 given one. Okay, so because all of these guys are the same, they're equal to 1/2, we're going to basically end up with that the probability that they are male is just equal to the conditional density for male divided by the sum of the two conditional densities. Okay, if the probability of male or female were different, then these guys would be weighted in a different way. Okay, those are the values when we stick in the Gaussian distributions. We end up that the probability that this bear in particular is a male is it's about 54.5%. Okay, let's look at another data set. In this case, I looked at this US Army data set that we already looked at when we were considering when we were seeing continuous random variables. I'm going to, what I looked at is height and whether people were left or right-handed, where this was defined by asking them what is their dominant hand during writing. This is the marginal PDF of height. And these are the conditional PDFs of height, given that people are right-handed or left-handed. And very quickly, what do you notice? You notice that they're the same. So the marginal PDF is the same as the two conditional PDFs. There are not that many people that are left-handed. So actually about, I think it was like 15% of people are left-handed. So the data for the left-handed people is a little bit noisier, but still. Okay, so now we can compute the conditional probability of being left or right-handed given height. And what we see is that it's almost constant over here, and it's a little bit noisy here and here, which again is normal, right? Because when we compute this, we're using data from a very, very small number of people. So in order to compute that, we use data from a very, very small number of people, so that's why it's pretty noisy. In general, what we see is that the probability of being right or left-handed is almost constant and unequal to the margin. So what does this suggest about whether height and handedness are connected or not? It suggests that they're independent, right? Like if I tell you that someone is right-handed or left-handed, it doesn't really change the information. It doesn't provide you any information about how tall they are, which makes sense, or at least it makes sense to me. I have never looked at this data, but it turns out that at least for the US Army, there's no connection between being tall or not and being left or right. In some contrived cases, there could be some connection because you might, for example, I don't know, have a lot of left-handed people because they play basketball really well, and because like being left-handed is a little bit of an advantage for sports. So then this could bias left-handed people to be taller if the army had like a basketball team or something. I don't know. I'm making up an example where there could be some contrived situations where these things could be connected. In this case, they're independent. We say that two random variables C and D are independent if our uncertainty about C does not change when information about D is revealed. Same way the other way around, right? Like our uncertainty about D is not changed when information about D is, sorry, let me repeat that. Our uncertainty about D is not affected when information about C is revealed. In the case of, if you remember, in the case of continuous random variables, and in the case of continuous random variables, our condition for independence was that the joint PDF had to factor into the marginal PDFs. In the case of discrete random variables, the joint PMF had to factor into the marginal PMFs. Here we don't have a joint PDF, we don't have a joint PMF, but we have conditionals, right? And we say that a continuous and a discrete random variable are independent of each other if all the conditionals are equal to the marginals. All the conditional PMFs are equal to the marginal PMFs, and all the conditional PDFs are equal to the marginal PDF. And that's what happened for the height and handedness data set, although, it's real data. So because of the limited number of data, the conditions weren't exactly the same, as often happens when we look at real data sets. The same thing happens if we want to condition on a third random variable, in this case A. We say that a continuous and a discrete random variable are conditionally independent given A if our uncertainty does not change when information about the other random variable is revealed, as long as A is known. And to capture this, we say that the conditionals between D and C are equal to the marginals when we also condition on A. Okay, always also conditioning on A. Okay, that's how we define conditional independence for discrete and continuous random variables when we model them together. Okay, so what have we learned? We have learned how to jointly model discrete and continuous quantities within the same probabilistic model. And we have also defined independence and conditional independence for discrete and random variables. Thank you very much.